Hi folks, this is a video walkthrough for the 2018 Acids and Bases Level 1 Science paper. Hopefully this will help you to understand some of the concepts and ideas that you'll need for your exam. So question 1 gives us three different models of atoms, and we're asked why are lithium and sodium in the same group of the periodic table but in different periods or rows. Well, looking at a little excerpt of the periodic table, we can see that the groups going up and down the way, lithium and sodium are in the same group because they have similar chemical behavior, and that comes from the fact that they both have one outer electron in their valence shell. By losing that electron, they both form ions with a +1 charge, and that is why they have similar chemical behavior. But they're in different periods. Well, the periods are different because lithium has 2 electron shells, and the periods relate to the number of electron shells for that atom. And sodium is in the third row, so because it has 3 electron shells in its structure. And that answer that I've given would be at about a merit level in terms of the exam. On to part B. How can sodium and fluoride ions have the same electron arrangement but different charges? In your answer, you should refer to the number of protons, charge, and electron arrangement of the two atoms and ions. Well, fluorine has 9 protons and 9 electrons arranged with 2 in the first shell and 7 in the valence shell. So it only needs 1 more electron to get a full or stable outer shell. To make a fluoride ion, it gains 1 electron, giving it 9 positive and 10 negative charges. So there's an excess 1 negative charge, which gives it overall -1 charge. Sodium, however, has 11 protons and 11 electrons in its atomic state, and they're arranged 2, 8, and 1, so 1 in the outermost shell. To make an ion, it's going to lose that outermost electron, leaving it with the electron arrangement 2, 8, the same as the fluoride ion. That gives sodium 11 positive charges and 10 negative charges. And because it's got 1 more positive or proton than electrons, then it gets an overall +1 charge. Now that answer would be around about an excellence level in your exam. In part C, we're given a formula, magnesium fluoride, and we're asked to explain how the ratio of ions in the formula is linked to the charge on the ions. So magnesium has an electron arrangement of 2, 8, 2, so it's going to lose those outermost 2 electrons to form an ion with a +2 charge. Fluorine, however, has got an electron arrangement of 2, 7, so it's going to gain 1 electron to form an ion with a -1 charge. And so what's going to happen is magnesium is going to lose its 2 electrons, and 2 fluorine atoms will pick those up and form fluoride ions. The net negative charge on the fluoride and the net positive charge on the magnesium ions cause a force of attraction to be experienced between both of the ions. So since magnesium becomes positively charged, it will be mutually attracted towards the negatively charged fluoride ions. As the charge on the magnesium ion will be +2, 2 fluoride ions are required to balance the charges, resulting in an ionic compound with no overall charge or a neutral charge. These charges indicate the number of outer electrons lost or gained by each ion. So MgF2, we can see that the 2 indicates that 2 electrons have been lost by the magnesium, and that 2 fluoride ions are required to balance that charge. Since magnesium loses 2 electrons and fluorine gains 1, they then bond in a 1:2 ratio, as seen in the formula. And that's an excellence level answer. I've just added this little note at the bottom. Ionic compounds again have an overall neutral charge due to this total loss and gain of an equal number of electrons. Okay, on to question 2. We've got solutions of potassium hydroxide, KOH, and sulfuric acid, and they're being added together in a beaker. Name the type of reaction occurring. So you should identify that hydroxide is an alkali, and acid, as the name suggests, sulfuric acid is an acid. And so when we've got an acid plus a base or alkali, we get a neutralization reaction occurring. So we're just looking for a one-word answer there, neutralization. That would be an achieved level response. So here we're asked to write a word equation and balanced symbol equation for the reaction. This is a really important skill. It quite often appears at least once and often twice in the exam. So for the word equation, you need to take the names of the chemicals you've been given in the question. In this case, that's potassium hydroxide and sulfuric acid. And then we're expected to be able to work out what the products are going to be. So because it's a hydroxide and acid reaction, we should know that one of those products will be water and the other product will be a salt. We get the name of the salt from the metal in the hydroxide, so that's potassium, and the other part of the name comes from the type of acid, sulfuric acid, giving us a sulfate. And so the name of the salt is potassium sulfate plus water. That's an achieved level response, the word equation. The symbol equation is a merit level response, and if we can balance it correctly, then that should be an excellence. So here's the start of the balanced symbol equation. We've got the formulas that we know were given in the question, and we need to work out the formula for potassium sulfate. So we can look at the resource booklet and take the symbol for potassium and its charge, and we know that that's a +1 charge, and the sulfate is a -2 charge. So from that we should be able to realize that the potassium, to form a +1 charge, is going to lose 1 electron, and in order to balance the charges with the sulfate for the -2, the potassium is going to have to give up 2 electrons to the sulfate. Potassium only being able to give up 1, it only forms an ion with a +1 charge, means that we'll need 2 potassium ions for each sulfate ion, and so our formula would be K2SO4. The other way of doing that is to write down the chemical name for the compound and the symbols and charges for the ions or ionic groups. And then we do the swap and drop, we drop the charges down, and because sulfate has more than one element in its ionic group, we put brackets around the outside, and so that gives us K2SO4 in brackets with a 1 on the outside. Now I wouldn't normally include the 1, but I've just included it here to try and convey full understanding. Once we've got the single charge on the outside of the brackets, we can drop the number 1, and we can drop the brackets, and that leaves us with the final formula K2SO4. Okay, so we can put the formula for potassium sulfate into our symbol equation along with water, which we're expected to know. Of course, you could work it out, but I think most of us would know that one. And then the last stage of this is to balance the symbol equation. So what I would do here is I would start from the left-hand side and I would count up the number of each individual element and total them up on the left-hand side and the right-hand side. And if they don't match up, then we need to put a number in front of the compound to do something about that, to balance the number of each element on each side of the equation. So we can see on the left-hand side here we've got a single potassium, and on the right-hand side we've got 2. So the only thing that we can really do about that, because there's no other potassiums anywhere else in the equation, is to put a 2 in front of the potassium hydroxide. Okay, so now the potassiums are balanced. We've got 2 oxygens here now because there's a 2 in front of it, and 4 oxygens here, so that gives us 6 oxygens on the left-hand side and 4 and 5 on the right-hand side. So to make up 6 on the right-hand side, We can't really do anything about the potassium sulfate because that would create far too many oxygens in this case. But if we add another water, then that would give us one more oxygen, which would balance the number of oxygens. So we'll go ahead and do that. And that's now the potassiums and oxygens balanced. Hydrogens, we've got 2 here plus 2 is 4 on the left-hand side. And we've now got 2 lots of H2O, which is 4 hydrogens on the right-hand side. So the hydrogens are balanced, and the sulfate groups are balanced as well. So we should be able to confirm that that equation is correctly balanced. And if you can get to that stage, then that is an excellence level response. Okay, in part C, we're told that potassium hydroxide is in the beaker, universal indicator has been added to it, and that starts off purple, and then sulfuric acid is slowly added until no more color changes are seen. And we've got to explain what's going on with the color change, relating it to concentration of ions and the changing pH of the solution. So in this one, I've put together a few little diagrams to try and help convey what's going on. At the start, the pH is going to be about 13 or 14, so it's greater than 7, and that means that there is a much higher ratio of hydroxide ions to hydrogen ions in the solution. And so that's what it might look like in terms of having more hydroxide ions than hydrogen ions. Bear in mind this is a very simplified diagram, and in actual fact the numbers of ions that you'd be dealing with are much more extreme. By the time that solution has reached neutral pH or green in color, then the number of hydroxide ions and hydroxide ions would be balanced. So you'd have approximately the same number of each, giving you the pH 7. And then as the sulfuric acid continues to be added, the number of hydrogen ions with respect to hydroxide ions would greatly increase. So you'd have far more hydrogen ions than you would hydroxide ions in the solution. And that means that the pH is now less than 7, and the number of hydrogen ions would continue to increase, or the ratio of hydrogen ions, I should say, to hydroxide ions would continue to increase as you went down through your orange, your yellows or oranges, all towards your pink and your red. So in terms of how I would word that answer, the indicator color would begin as purple, somewhere in the pH range of 12 to 14. There's far more hydroxide ions in the solution than hydrogen ions. As we add more sulfuric acid, the ratio of hydroxide to hydrogen ions decreases, and the color would change towards green, getting towards pH 7. At this point, there are an approximately equal number of hydroxide and hydrogen ions. Once the solution has become neutral, adding more sulfuric acid raises the ratio of hydrogen ions compared to hydroxide ions, reducing the pH further and changing the indicator color from green through yellow, orange, and finally getting towards pink and then red. Once the indicator is red, the number of hydrogen ions is far in excess of the number of hydroxide ions, and we would say that the pH would be around about a value of 1. So if you can do that, then that would be an excellence level response. You don't need the diagrams, I've just included those to try and help you understand what's going on in the solution. Okay, question 3. So here we are with another word and balance symbol equation. This time it's nitric acid and magnesium carbonate. We haven't been given the formulas for those, but you should know all of your acids, your 3 main acid formulas. That's hydrochloric, sulfuric, and nitric acid. And we can work out the magnesium carbonate nice and easily. So the word equation to start us off with will be magnesium carbonate plus nitric acid. Because it's a carbonate reaction, we should recognize that that's going to produce carbon dioxide and water as well as a salt. And the salt in this case is going to be magnesium nitrate. So again, taking the first part of the name from the metal, and then the acid gives you the second part of the name of the salt, so magnesium nitrate. That's achieved level if you can get the word equation. Getting the balanced symbol equation, well, we'll get the symbol equation first. Magnesium carbonate, the formula's there, and the way that we would get that is by looking up our resource booklet. We would see that the charge on magnesium is 2 plus and the charge on carbonate, the carbonate ionic group, is 2 negative. So they're going to join in a 1-to-1 ratio, giving us magnesium carbonate. You can also do the swap and drop, which I'll go through here. So we write down the charges, we then drop the charges down, putting brackets around our carbonate. We've got to be very careful with that. Because the numbers are the same after the magnesium and the carbonate, i.e. they're in the same ratio, we can drop the numbers down to MgCO3. The nitric acid, I've written in there for you, it's HNO3, and a reminder that you're expected to know the 3 formulas for your acids: nitric, hydrochloric, and sulfuric. For magnesium nitrate, we can see the charges on the magnesium are 2 plus and on the nitrate is a single negative charge. So here we're going to need 2 nitrate groups to balance the charge with the magnesium, and so the formula will be Mg brackets NO3 close brackets 2. We can get that with the swap and drop method again, by dropping those charges down, making sure we put our brackets around the nitrate group, and then we can get rid of the 1 after the magnesium. Okay, so then we can write that formula in along with carbon dioxide and water, which I'd expect you to know. And then we need to balance the symbol equation. So starting from the left, we've got 1 magnesium, 1 magnesium. We've got 1 carbonate group, or 1 carbon I should say, and then 1 carbon over here. We've got 3 oxygens plus 3 is 6, and over here we've got 6 oxygens altogether in the 2 nitrate groups, plus 2 is 8, plus 1 is 9. So we're going to need to add some more oxygen to the left-hand side. We probably don't want to be adding any more magnesium or carbon, as we've already seen they're balanced, and so we're going to add another nitric acid, and then we can just check that that is balanced because we've now got 2 hydrogens on the left, and we've got 2 hydrogens on the right. We've got 2 nitrates on the left and we've got 2 nitrates on the right. Just be careful and check that if you're not sure how you work that out. We've got NO3 in brackets twice, and so everything in the brackets is doubled, which means we've got 2 nitrogen and 3 oxygen doubled is 6 oxygen there. So 2 nitrogen on the left, 2 nitrogen on the right, 6 oxygens now here, plus 3 is 9, 6 oxygens plus 2 plus 1 is 9, so everything is correctly balanced there, and that would be an excellence level response. Okay, total mass of the flask and its contents is measured over time and shown in the graph below. Why does the mass of the flask and its contents decrease during the reaction? So remember that the conical flask it was stated in the question that it was open, and in our previous answer we identified that carbon dioxide was one of the products, so it's a gas. Because it's produced as a gas, it can escape the flask, and so because the conical flask is open, carbon dioxide produced during the reaction will be lost from the flask, which reduces the mass over time. And that is a merit level response. For B part 2, we're asked to explain what's happening in sections A, B, and C of the graph, and we're expected to link our answer to rates of reaction and particle collisions. So in section A, we can see that the line is steepest, which indicates the biggest rate of reaction, or the highest rate of reaction, as the mass of the flask and contents decreases most rapidly. And so the concentration of reactants is highest at the start, the very start of the reaction in section A. And so from the very start of section A, there will be more successful collisions between particles, creating products. This high rate of reaction can be seen in the steepness of the line, and that's just because you've got the most reactants at the very start of the reaction, because none of them have been used up yet or converted into products. Obviously over time that changes, and that's why we can see the steepness of the line in A gradually decreasing as reactants are used up and products are formed. The concentration of reactants decreases, meaning that the rate of reaction, the number of successful collisions per unit time, and therefore the rate of reaction decreases. So that takes us into section B. So as products are formed, the concentration of reactants decreases. That means that there'll be fewer successful collisions between particles per unit time, and so the rate of reaction slowed. And we can see that in the shallower curve at the start of section B. By the end of section B, the line's horizontal, and that continues through to section C. At this stage, once the line's horizontal, all possible successful collisions between the reactant particles have occurred. Now, this can happen because either one of the reactants has been completely used up, or both of the reactants have been completely used up. Because no more successful collisions can take place, no more reactions can happen, and the rate of reaction has stopped, or the reaction has stopped. And that's shown in the horizontal line on the graph. And that also means that the mass of the flask and contents of the container are no longer changing because no new carbon dioxide is being formed. So if you get all of that, that's an excellence level response. Okay, on to part C. Explain how increasing the temperature will make the reaction between magnesium carbonate and nitric acid faster. So you're expected to know that increasing the temperature will increase the kinetic energy of the particles, giving them having more kinetic energy means that they will move more rapidly and collide more frequently and with higher energy. That increases the rate of successful collisions, which increases the rate of reaction. And that rather short answer should be at an excellence level. Okay, I think that's all for this paper. I hope that's been useful to you. Let me know if you've got any questions. Thanks for listening.